Well, after a couple of false starts, I think I've got a video for you to look at today and a problem to work on. So I have a couple of reminders about some of the types of equations we were learning before we went off on break. If you recall, the first and second order integrated rate law expressions are really important. And if you look at some of the solved problems that I've posted on Sakai, you'll know that you have to use these equations quite a bit when you're doing a kinetics chapter. This one here reminds you that if you take a natural log of concentration versus time, in this case they divide by the original concentration, it really doesn't matter very much, you can get the rate constant by calculating the slope. In the second order integrated rate law equation, you need to plot 1 over the concentration at various times t versus t, and you get a slope for that as well. Very, very useful. Well, you can get other kinds of second order reactions, but in this case, they're first order in 2 different reactants. So imagine you had a reaction A plus B, and the rate of the reaction was first order in each. If you remember, we did differential rate laws to look at the rate of the reaction in terms of the loss of one or the other reactants, and you can come up with this expression. Hopefully this is something that you can remember. If you can't, the expressions in these derivative forms are in the earlier part of chapter 15. There is a note here for this derivation that I'm about to take you through. It's going to requiring us to assume that the original concentrations of A and B are not equal. If they were, the math would basically reduce to just pretending they were the same thing. Even though the A and the B are different molecules, the kinetics would work out as if they were exactly the same. So we're not going to do that. We're going to assume that we have a concentration of A and B that start out being different. So I say here, let's say that when A, so whatever it is, has dropped to the original minus some amount x, well then the original of B minus x is going to be the concentration B. You might recall that I think in class previously I would put little t's down there to say it's the concentration of A or B at time t. I'm not going to do that every time. It just seems like it's a little bit unnecessary. But let's make that assumption, that after the reaction has gone on a little bit, the concentration is going to be whatever the original is minus some amount x. This is going to become important when we do our derivation. So notice the substitution I've made. So if you look at the previous page, you'll see that I had a relationship for the rate of the reaction in terms of the change in A. The change in A is going to be related to the concentration of A and B at any point along the way. And so based on that definition of x I gave on the previous page, you can make a substitution into the expression. Now here, we want to think about how this value x, the amount that reacts, is related to the rate of reaction. Now simply because of the stoichiometry, in other words, if 1A reacts with 1B, then the amount x that you're subtracting from the original A is equal to the rate of change. It's going to be related to the rate of change of A. Let me say that again a little bit more clearly. As A is decaying, that is obviously going to be related to the amount of x that reacts. And so this expression becomes true. So the change in A over time, remember that's going to be a decreasing number, is going to be the amount of x that reacts, this is a positive number, multiplied by a negative 1 is going to be exactly the same. So this expression here is represented in a differential form over there. And so if that's the case, I can write the rate law not only in terms of A, like I did before, but I could write it in terms of x, the amount that reacts. Now we know the amount of chemicals that react has a connection to the amount of A you have and the amount of B. And so that's where this expression comes from, that the dx by dt is going to be equal to this expression, which is related to the one above. So now here's where we're going to try to get an integrated rate law. I'm not going to make you do this integral. I'm just going to show you how it's done. That's why I say we sort of integrate. Now, given the initial conditions that before this reaction starts, x is 0 because nothing reacted at t equals 0, therefore the integral becomes, I'm going to integrate all the pieces that have x in them from 0 to x, that's the left-hand side, and the remaining pieces, including anything involving time, is on the right-hand side. And so that's going to start from 0 to t. So this is the integral we need to solve. Now, I'm not going to make you do that. I'm basically just going to use, from a standard table of integrals, what this integral looks like. And the technique from your calc class was called the method of partial fractions. I'm not sure you did this one when you took calculus, but I think I remember doing it myself. So that let me rewind here. This standard integral form in blue, that's out of a calculus book. So the A's and the B's don't know anything about chemistry. They just happen to be the same letters. I just want to make that clear. So everything in blue here is just the standard calculus form. We're going to apply our chemical integral to this blue form. And I do that here. Notice that having the advantage of these two different colors will show you this. So I took the chemistry pieces, the A naught, the B naught, 0, and x, and plugged them into this standard calculus integral, and I got this reaction. And if you stop the recording a bit, I'm sure you could do it on your own. It's not really that tough. But if you get this expression, and then remember that the definition of, let's say, b at any point is the original minus some amount of x, you could actually make this equation here look a little cleaner. And in your textbook, this is equation 15.4. By the way, anything that I'm saying here, you could follow along in the textbook, and they use a slightly different order or emphasis. But really, all of this work that I've been putting together is to get equation 15.4. This is the integrated second-order rate law for a reaction of A plus B. Now, you might recall that we can get information from these integrated rate laws by making plots, like I did on the first slide. We could do the same thing here. If you make a plot of the left side of this reaction versus t, you should get a straight line. And that slope can help us get information. And we love in kinetics getting rate constants, and that's what we have here. The rate constant is simply going to be the slope of this plot divided by the difference between the original concentrations. Let me show you an example. So here's a brief illustration. So let's say I have two reactants. The original concentration of A is 0.075, and the original concentration of B is 0.050. And after 1 hour, whatever technique you use tells you that the B concentration is 0.020. What is the rate constant for a reaction like this? Well, because of the stoichiometry, we kind of went over this before, is 1 to 1, it follows that X is going to be the difference of the original concentration of B minus the concentration of B after the hour went by. And so the X here is 0.030 molar. I'm going to use that X to figure out the concentration of A after 1 hour. So I took the original, which was 0.075, minus X, and I got the concentration of A after 1 hour. Well, that actually does a lot of the work for us, because from equation 15.14, I know a lot of those variables. I know all the original concentrations, I know the concentration after 1 hour, and I know that 1 hour converts into 3,600 seconds. I think kineticists are kind of biased toward having time in with inverse seconds. People who do archaeology might use years, but chemists usually like seconds. So if you churn through that math, you get a rate constant of 4.5 times 10 to the minus third inverse molar inverse seconds. So I hope you do that math and work through that to see you get that. Notice the unit should make sense to you. Remember we said when we were first learning kinetics that the rate of a reaction is always molarity per second. And so if you have a rate constant times two concentrations of molarity, well then you know that the units of the rate constant have to be inverse molarity, inverse seconds. Now I came up with a problem for you to do. Let's take a look. So the second order rate constant for this base reacting with this ester is, here I'm giving you the rate constant. It's 0.11 inverse molar inverse seconds. I'm asking you to figure out the concentration of the ester after 20 seconds and after 15 minutes if the original concentration of the base is 0.060 and the original concentration of the ester is 0.110. You might need a couple pages of paper for this. The math may be a little hairy, but I did it just now and it does work just fine. So good luck on that, and we'll see you tomorrow at 11:30 a.m. Bye-bye.